And on my end, I'm
Good. Let's get started then. This is the first live stream, so I think we should just take it lightly, I would say, and not have it be as too much.
yeah, I think I'm probably gonna like basically just give an overview of the contents of the paper, give a little bit of background info on like what manifolds are, what tensor and exterior products are, what differential forms are.
Yes,
It's gonna be a very light overview.
There we go. I think everyone I could. I'm going to put as the title of the stream the title of your paper, and for everyone who somehow hasn't realized it, yes, this is about a paper that Silver has written, and as such, I will put a link to it right away on the very beginning in chat for everyone to grab, and I'm going to do this. Beautiful. And people are already joining in.
Oh, where's it at?
So hi Joel, hi Driblax, hi Georgios, hi, welcome. Okay.
So where's the stream at? Is there a link somewhere?
Yeah, I've linked it both in the make it and in the library. I've sent the link.
Okay.
I can ping you if you'd like to.
Yeah, that will work.
This is the stream. I almost didn't make it in time. Fortunately, here's the one place where you always make it in time.
Make it make sense, make it happen.
Well, honestly, Silver, this time you'll have to make it make sense. Because I don't get it. It is... Your profile picture very much matches to how I view your paper.
There. Okay, so... So I guess we could start. So first off, basically, the premise of a manifold, or I guess specifically a smooth manifold, is you have a topological space. Say you have some like... Hopefully this won't have too many discrepancies with reused notation, but so say you have some topological space. It's like a pairing X. So it's like a set of points, and then you can either describe it with like a set of neighborhoods in that space, or with one second, sorry, or with a topology, which basically there's like different types of topologies they can put onto sets to make like topological spaces. In our context, we don't care about the specifics of that. What we do care about is it's specifically a topological space that's locally homeomorphic to Rn. One second. Okay.
All right. Yes, so everyone watching, you will have to excuse at least a bit. This is the first stream after all, and so we're also kind of trying to figure out how this goes. And since it is the intermission, I'm going to take this time to once again remind everyone that the paper does exist on the website, and I would recommend checking it out. This is it. This is the paper we shall be discussing, written by Silver. It contains a lot. It contains, in fact, a lot, and a big issue is that I myself am not particularly mathematically inclined. I don't really have many mathematical skills. I ain't some big smart talking fancy mathematician. And so I have absolutely no idea about most of this. And so this is all just an elaborate scheme set up by me in order to finally understand the absolute witchcraft that it is, that musical isomorphisms I've had the fortune of Silver explaining to me in the past, so I kind of get them, but differential geometry has a reputation. T acquired. Alright, perfect. We're right now experiencing a bit of an intermission, because it just takes a bit. And so I am giving context to everyone, just in case someone missed why this live stream is happening. This is the paper. Should we reserve chat only questions? Don't have to hunt for questions in the chat. I don't think so. Don't worry. Since Silver will be the one presenting, I can just look through the chat for questions, and as they happen, interrupt to ask them to Silver. So nothing should really be missed. I should catch all of them. You don't have to keep them only. Oh, but this is incredible. I mean, this is just LaTeX wizardry right here.
All right.
Okay, beautiful.
So, first, can you hear me all right?
Kind of in a way. It's a bit... You sound as if you've moved away for a bit from the mic.
I had to move to a different room.
Okay. Do you think you could move a little bit closer? Because I worry this might make this a bit difficult to understand.
Yeah, just a sec.
Actually, Roblox already asked a question of when
Better?
those not entirely, but well, worst case scenario, we can proceed a bit and then see how it goes.
Yeah.
If you're understandable enough.
Testing, how's this?
Oh, this is brilliant. Very clear.
Okay. So, we have... I'm going to delete this. Hold up. We have topological space, and we can equip it with what's called an atlas of charts. A chart is a pairing where we have any given open set on the space, and we have a diffeomorphism, which is in a way kind of like a smooth map, like a smooth invertible map. So yeah, it's like a pairing. So the atlas is the set of all the, I guess, charts. Sorry, my handwriting is awful.
It's fine.
So what we can do is, if we have a, I'm going to draw this out. If we have a specific patch on the manifold, like say this is our U, then we have the map to some subset of Euclidean space. And this is psi of U. And this is Euclidean space. And the basic premise of this is it allows us to do calculus on it, because most calculus isn't really well defined on curved spaces, but being able to convert it to a non-curved space essentially gives us that freedom.
Mm-hmm.
Okay. You know, it'd be really helpful if they had a way to just like erase a bunch of stuff at a time.
You can just select the whole bunch and you can press delete.
Okay. For context, I'm on mobile, so I can't.
I can delete it for you, like.
Okay.
Just let me know when.
Okay. So now, 1 second. So now, first off, we start with tangent vectors. So at a point, I'm just going to draw up some arbitrary manifold. at a point, I guess in some chart, we kind of need the chart for this, but also technically not. We have what we call the tangent space, which there's also ways to define it. The two main ways are either through the space of derivations around the point, which basically if you have any function, like if you have like a linear map D where it follows like a specific product rule, kind of like a derivative. Hold up, I'm writing this. GDF plus FDG. Basically, get that. We can like define the space of derivations around this point, which we can denote. Hold up, it's been a minute since I've written this. dp m. I'm gonna use m for our manifold and like for the rest of this.
Mm-hmm.
So we have that, and we can prove that there's an isomorphism wrong between that and the tangent space. So we can sort of define the tangents. We can sort of like use this isomorphism to define tangent vectors as derivative operators at the point. So any sort of like linear combination of partial derivative operators at the point is an element of the tangent space. Second, I'm just gonna see how chat's doing right now.
Okay.
To answer Reblex's question, the pentagons, they were actually, like in the document, they were actually like given to me from somebody else who had written them, or I guess who had made them. And I believe they're just in plain text. All right, continuing on. We can then construct what's called the tangent bundle, which basically is the collection of like every pairing P, T, PM, which, or I guess we would take the disjoint union of it, of like each one. So we have at each point a vector and like the point of interest, which I don't know. I don't really think I could explain fiber bundles or vector bundles like do them justice off the top of my head, but I can say that what the advantage of this is it lets us create vector fields. Also, there's a way of defining tangent spaces through equivalence classes of curves. I encourage all of you to look for sources on that, since it's a bit easier than the whole proof of this isomorphism between derivations and tangent spaces. But those definitions are equivalent. So yeah, basically we have the tangent bundle where at every point we have a tangent space, we have our tangent vectors. And so then anything of the form D or del x mu is a vector field. So if you want to delete all of that, make it.
Mm-hmm. Absolutely everything? Right.
Yep. So if you have our manifold, 1 second. Then we can have a vector field, a tangent vector field on the manifold. And we also have a dual to the tangent space, and then we can construct from that a dual to the tangent bundle. We have the cotangent bundle, TP star of n. In this, we have linear operators that we denote dx. And it could be anything like dx, dy. And what it does is if you have dx, like if you have like dx1, for example, and you have some vector field x, then it gives you it just gives you the first component of the vector field. So, for example, dx of 3x partial x plus 2y is just 3x. Again, I'm kind of speeding through this a little, not because I intend to, but because lots of this stuff is kind of hard to go into great detail about without like a textbook.
Okay.
Is everything good so far, by the way?
I mean, as far as the bits I'm catching, I would say yes. The speaking
Okay.
through it a fair bit, I understand, but it does make it just a
Yeah.
little bit difficult to.
Yeah, I'm trying to pace it a bit better.
I mean, I suppose that's more of a question to Rebecca Joel and I suppose Ash couldn't
Yeah.
join it, but more to them because then.
Yeah.
So to you all watching, is to us, Rebecca said you could give the geometric intuition of vector bundles.
Okay, so I don't know how to explain it. I mean, I kind of understand vector bundles through my understanding of fiber bundles. I think that could probably be useful. Basically, the premise of a vector bundle is like if you have some space, I'm just going to draw a curve here. 1 second. Like at every point, you can assign a vector space where locally, if you zoom in, it's like locally just a product of the vector space and the topological space that you're on. So it's almost like you have your vector space, topological space, and locally it looks like basically the product of the base space and the topological space. Globally, it doesn't have to look like that. Like, for example, in the case of the Mobius strip, locally, it looks like a product of like a line with another. But globally, you have the issue with where it loops over. I'm not going to attempt to draw a Mobius strip, but with the loop, it stops looking like that. Any sort of like Cartesian product of spaces is what we call like a trivial fiber bundle.
That I think makes sense. Yes.
And then, so basically, we then have these projection maps. I'm going to denote it pi, where they basically send elements of, I guess, like they locally send elements of the bundle to the base space. And then we have inverses of them, which are called sections. I'm denoting them sigma, right? Where if you take pi of sigma of some element, or I guess of some point on the vectors on the base space, then you just get, like if you take the projection of the section I don't know if I'm phrasing this right. 1 second. Basically, projections and sections are inverses, and you I'm trying to think of how to phrase this. You realistically would get a point on the base space back. So then, essentially, vector fields are these sections because they send a point on the manifold to one of our tangent spaces. Okay.
Mm-hmm.
And then a global section is, or I guess I should say global section is what a vector field is. And if you want to erase all that,
What I would do
so
is raise the top and keep the bottom like small.
okay, I'm just looking at chat. Okay. All right.
So far as Reblax giving you seal of approval.
Yeah. Then we have, so say we have two manifolds. Like, I'll make this a bit bigger actually. 1 second. So we have a manifold M and a manifold. Actually, no, it's and a manifold N. We have tangent space at a point on M. That looks weird. And a corresponding tangent space at a point on N. Let's say we have a function f. Then we can define what's called the push forward or the differential of f, which we can either denote df, tf. There's lots of notations for it, or df, usually like at a point. Sometimes it's denoted dpf. Then that maps this tangent space to this other one. In other words, we have t. It maps tpm to tf of p n. All right.
Right, that makes sense.
And yeah. So this basically just allows us to interpolate between tangent spaces, different manifolds as we need, whatever purpose it may be for. It's also sometimes denoted as f. Oh, wrong color. Whoops. Sometimes denoted as f with a superscript star. So, for example, if we have, or I guess real quick, a way we can think of it is if any of you remember like the Jacobian from vector calculus, then is like if you can represent your vector as like a column matrix, then it's basically just your Jacobian matrix times your vector. Okay. So it's basically a linear transformation that like smoothly varies from point to point. And if you want to shrink that,
Yeah. Keep for later.
yeah. Then we also have something called a pullback, denoted with f subscript star.
Also, Reblax just said f star is for differential forms and goes the other way around, doesn't it?
Oh, I got the star wrong. The star for the push forward is the subscript. Or
So like this.
no, yeah. Yeah, this subscript stars for the push forward. The superscript stars for the pullback.
I have a
So,
feeling that like whenever people were coming up with notation for this stuff, they were doing so with a big grin on their faces, to be honest.
oh, definitely.
Because it
So,
having yeah, okay, go on.
the pullback is contravariant in a way where it maps T of F of T, no, T star F of P, so the cotangent space on N, to the cotangent space at a point on M. That looks weird. Okay. So what it does is in the base case, so you have a function g, then f star of g is just g of f of whatever. I guess you could do the circle notation for composition. And then in the case of a covector field is what, like a smooth covector field is what we call a differential one form. So the f star of omega, like omega is any like it's any linear combination. It could be like basically anything of this form if we're saying it's a one form. Then this is if it's acting on a specific vector, then we have omega is it's basically just omega of the push forward of this. In other words, f star dx m equals dfm, because we can basically, like, if we can represent like the linear transformation, like if we can represent, I guess 1 second, I'm trying to collect my thoughts here. If we can represent f with, say, a vector of like functions, almost like, because like it's almost like the parameterizations you see in vector calculus. It's like like a linear combination of like, I guess like a vector of different functions like this, like f equals f1, f2, blah blah blah, and then yeah, it's like f1 of x1, x2, blah blah blah. Then you basically just take the total differential of this, which is that. So basically we have the pullback of a form acting on some vectors is the form acting on the push forward of those vectors. Okay, if you want to shrink or delete whatever you need.
You're just putting it all on screen first, alright. I can
Yeah.
just right here then.
So yeah. Then we can, and then if we want to like I guess some of these up a dimension, like if we want one like the differential K vector fields, we need the wedge product. So first off, if we have some vector spaces, we can find a floor product or free product, you know, like this. We can do vector spaces. And then you have like, if you have some element V star W in making a very obvious push on lowercase and capital.
I appreciate
So
it.
this product, it's kind of hard to explain. There's plenty of good resources on it, but I like to think of it as nothing from this can cross over to this without it being like a different thing, if that makes sense.
Could you go a bit more in depth on that?
So I'm trying to think of how to explain this. So say you have like the formal product of some basis vector E1 with some basis vector E2. You can't really, in any normal sense, have like bring this over to this side of the product. You can't have like one, at least without defining anything else. You can't have one E1, E2. It's basically just you can't.
Yeah, that makes sense.
Without certain without the tools necessary, you can't multiply vectors and get higher dimensional things.
Yeah, that makes sense.
I'm leaving out some details, but again, it's mostly like there's like some sources online that you can find. There's a really good Michael Penn video that describes this formal product or free product that I'll send somewhere like after the fact.
Also, Reblex just asked, is that the amalgamation product of groups?
I believe it's similar, if not the same. I'll check real quick. Co-products in the category of groups. Yeah, it seems like the same thing roughly.
Well,
I'm not assuming anything yet, Roblox. Okay, so next step. So we have what we call quotient spaces, which is a much more of a linear algebra thing. I'll give a quick rundown. So we have some vector space V, and then we quotient out some vector space I. It's basically almost like a way of like gluing. One second, I'll be right back.
Swift intermission. Okay. Great. In the meantime, as soon as we can, yeah. I can All right, great. I can scroll through the paper yet again, go through it slowly. Maybe with the context given on stream right now, I will be able to understand a little bit more, hopefully, fingers crossed. Man can dream. All right, brilliant. So.
Okay, I'm back.
Very swift information, all right.
I'm back. Okay, so if it would let me hit the draw button, 1 second. There we go. So I won't give all the details, but basically gluing everything together means we can identify it with any sort of value of sorts as we want. In fact, we could identify one advantage of it is we can identify any elements of this with the zero vector, because we're treating it as almost like an equivalence class. So when we take this quotient, we're forcing anything in here to equal 0. So what we can then do is, if we have I equal to I'm gonna pull up a reference image real quick, if that's okay.
Should be okay.
While I'm looking for, I don't know, I feel like I'm doing this kind of poorly. I'm trying my best.
Hey, first time presenting it, it's fine. It's fine. So far, it is also a very specific. I feel like you're making up for it with information, so don't worry. It is a very specific topic for a paper and presentation,
Yeah.
so I think the information alone is quite valuable.
So lambda star, or I guess, right now, lambda v star w minus lambda v star w v star lambda w minus I think. Yep.
Right.
I'll explain what all this means in a second. I'm just writing it out first.
No worries.
All right. So basically, if these look familiar, it's for a very good reason. These basically turn bilinearity into linearity. It's basically just saying, yeah, we want to restrict this product space to when elements of either like thing have these like bilinear relations, because like a minus b equals 0 means a equals b, so we want these things to be equal. Like if you see this on the left hand side of these differences, and on the right hand side of these differences, we're basically saying, if you like ignore that this is like like a set or space or whatever, basically getting these things to be equal to each other.
Yeah.
And that construction, if we have v star w with that quotiented out, then that is how we define the tensor product of these two things. If you want to, I'd say
A note from Reblax as well as the notation is sort of bad. You should really be taking the subgroup generated by what you wrote, but the idea is correct. You are imposing those relationships. Those relations, sorry.
Yeah. Again, there's places that describe this better. Yeah. Okay, so now, yeah, you can shrink that if you need. So now we can then define the exterior product of vector space with itself. We can't really define a vector space's exterior product with another vector space by taking tensor product of the space and quotienting out. Let's say we have this thing J. It's like a, I can't remember. It's like, I think, I can't remember. It's like a subgroup of sorts, I think. Where basically you have the set of any elements of the form V tensor product V, where V is of course in the original vector space V. What this does is why we want this is it allows, like one of the major principles of exterior calculus or exterior algebra where like anything wedged with itself equals 0. And also we then also have any like a property of anti-symmetry where wedge product of something with something else is the negative of the wedge product of that thing with the first thing. And I'll just rewrite this here too. Yeah, sub-vector space, like Redblack said. And if you want to shrink that down, okay. So then we have exterior powers of vector spaces. The kth exterior power of a vector space V is just V, wedge V, wedge, blah, 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 like K times. And so then we could take exterior products of tangent spaces, tangent bundles, cotangent spaces, or cotangent bundles. So then we get differential K forms and K vector fields by taking like linear combinations of these. We have anything of the form dx1 wedge dx2 wedge blah 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 plus dx. I don't know. There's lots of ways. There's like based on how the ways you can combine these things into wedge products. There's exactly like for any n manifold, the kth exterior power of the tangent bundle or the cotangent bundle has exactly dimension n choose k, which is, correct me if I'm wrong, but it's, oh, 1 second. It's this formula here, again, based on just how many ways you can combine these things. I'm just putting this in parentheses here. It's like, it could be tangent or cotangent. Okay, you want to shrink that down?
Mm-hmm.
All right. And then just as a side thing, it's got, like products like associativity, linearity, the usual things you'd want from a product in a case like this. Except it's not commutative, it's anti-commutative like we established. Okay, I'm trying to think of what to say or do next. I'm just gonna real quick check because I know I had written somewhere like a pretty concise explanation of this stuff over text in a server somewhere. Also, in a minute, I'll probably give a quick rundown of how to visualize these things because I think that'd be pretty useful. Okay, here we go. Yeah, I did that. Oh yeah. So then, if we have dx1 wedge dx2 acting on a couple of vector fields like x, y, I'm gonna denote it like actually like x1, x2. Then we get a determinant of dx1 of x1, dx1 of x2, dx2 of x1, dx2 of x2. There's a way you can like explain why this determinate way of doing things works, and this of course extends to any k form acting on some k tuple of vectors, or I guess vector fields if you want to be more correct. But anyway, that's how you actually evaluate them. And then you can also define something called a metric tensor, whose components are basically just the dot products of your basis vectors. I won't go into as much detail with this here as I could because it's kind of a lot to explain, but it basically allows us to measure things like lengths and angles, because basically if you have the matrix of all the components, then you essentially have the magnitude of each basis vector squared, and then you have other intermediate values between that basically can give that, like, you know, there's that one formula of like a dot b equals magnitude of a magnitude of b cosine theta, where theta is the angle between them. You can make use of that pointwise to get angles between your basis vectors. In classical Euclidean contexts, you're going to have all the basis vectors have length 1, and you're going to have all the other things be 0 because cosine of 90 degrees is 0, and you'd expect, you know, orthogonal things to be orthogonal. If you want to shrink all of that down. Okay. So, an interesting thing is so there's this relation where you can sort of define the matrix of the metric tensor as the transpose of the Jacobian times the Jacobian if you're, say, in a particular chart, or like if you have some way of parameterizing like some patch of your manifold, because you could technically extend this globally, but it would be a bit difficult. then you get sorry, I cannot speak. The determinant of G is equal to the determinant of the transpose of the Jacobian times the determinant of the Jacobian. I'm basically kind of like distributing the determinant in a way just because of basic linear algebra stuff. And then that becomes J. So basically you get the Jacobian determinant is the square root of the metric tensor determinant, which allows us to give a notion of, I guess, like infinitesimal volumes at like a point. In fact, we have something we can call a volume form, which is denoted in lots of ways, usually dv, dvol. 1 second. Which we define as this determinant square root times basically all our basis 1 forms wedged together, so we get like a top form of sorts in increasing order. And now I'm going to briefly explain like how to actually like integrate these things, because we don't just use dx for no reason. If you want to shrink that down. Okay. So now. Oh wait.
No, it's fine. You can start. I suppose drawing is just getting a bit of a nightmare to select.
Yeah.
There we go. For record keeping purposes, I just want to keep it. There we go.
Somewhere. That works. That works. Okay. So back to this. So first off, we need to define these things called partitions of unity. Basically, each partition of unity can be denoted rho j, such that and they're defined such that the sum of them over j is just equal to 1. There's lots technically there's lots of ways you can actually obtain these. The usual way is through bump functions, because you want them to usually drop to 0 after a certain point. So yeah, the usual process is defining some bump function. I'm just going to call it theta, and then I guess theta j, and then I guess doing a way of normalizing it, or I guess just getting it to not go beyond 1 by basically taking this sum of all the other ones. I think it's something like that. I could probably check real quick. I encourage all of you to check. But anyway, the point of this is, if we want to integrate our form over each chart, then it prevents overcounting, because if you have overlap, you don't want this extra room to count towards it twice. If you want to shrink that all down, you could probably tuck it away somewhere.
All right.
So then, if we want to take the integral of a form m over omega, we take the sum over some values j of the integral of patches u j of each corresponding partition of unity times the form. And then an interesting result I should also mention is another way we can define the pullback. This is relevant. I don't know why I didn't mention it sooner, but we can define the pullback through the relation. If you take the pullback, if you integrate the pullback of a form, you basically just integrate the form over the thing acting on the manifold like that. So that means we can take advantage of this. So you can imagine that the patch uj is just the inverse of the chart composed with the chart itself, because those would effectively cancel because it's bijective acting on the uj. So then we can bring this inverse up and get I guess psi j uj of -1j. This pullback here. Yeah, you might want to move that. I'll make that a bit less cluttered. Looks kind of weird. And then say you want to define your form omega like some sum over a value k of some functions phi k times, dx1 wedge dx2 wedge blah 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 all the way up to dxn. All right, need another wedge product. Then, yeah, I was thinking you could probably shrink that down a bit. Okay, there we go. Then you have this. I'm trying to think of how to explain this. Then basically, when you're integrating a form, you can essentially drop these wedges when, and I'll show you that in a second. So we have a sum of over j and k of, because of the way we defined the pullback initially, we get phi j of, not phi, rho j times each phi k composed with the inverse chart. And then we have, let's say, so I already used x for the coordinates on the actual manifold. Let's use y for the coordinates in our chart. I don't know, let's say we have our manifold. Let's 1 second. We have our manifold, and we have it going into Euclidean space. And then you have, on here, your coordinates are x1, x2. These aren't meant to be mistaken for exponents, by the way. And then on here you have y1, y2, blah, blah, blah. And then you have then you have essentially the determinant of the Jacobian, which is you can write as x. Yeah. Blah, blah, blah. And then you have your, you can imagine that, because of the whole -1. Actually, I might be doing this wrong. One second. No, yeah, I'm doing it right. So then you have dy1, dy2, blah, blah, blah. And then from there, it's just your normal integration that you'd see in any standard calculus course. If you want to shrink that down.
Intermission. All right.
Okay, so could you pull up the paper on the stream?
Yes, I can. There we go.
All right. So then in the actual paper, it's basically then using these tools that I've constructed here, we have a few other operators, you know, the star, the D, the sharp, the flat, and I could have also given a bit more justice to talking about the boundary operator. You can easily visually get some intuition of boundary operator, like on a curve, it's just the endpoints. On a open surface, it's just like a curve that you can draw around the edges. In a volume, it's just the surface on like around it. Like it's pretty simple. So basically, we have those, and we have a way of flip-flopping between vectors and covectors, forms and vector fields, k-forms, k-vector fields, k-forms, and n minus k-forms, and you know, getting a notion of derivatives in general of k-forms. And then with Stokes' theorem, which I prove in there, we get, you know, that the derivative is related to the boundary. And then we also can define a way of defining a norm or magnitude of forms and vector fields, but also k-forms and k-vector fields. And then, you know, we can get the classical results of vector calculus from a mix of Stokes' theorem and those other tools, and also two other things called the Lie derivative and the interior product. And I guess the main goal of my paper was to make these explicit because lots of documents talk about these things, but they kind of gloss over them or are really hand wavy with them. I was gonna give a quick snippet on the visuals, but I had out. I think that's all I really have to say for now. I'm just gonna quickly write something on the whiteboard.
That's absolutely fair. Yes, I mean the main thing was still in the paper itself, still available for everyone to check out.
Yeah.
On the website, and oh yeah, I wonder what you're going to write on the whiteboard, obviously.
Is there any way to download like these whiteboard things as like an image?
That is precise. Well, they're not really that I'm aware of. There might be actually. Oh, there is. Yeah, in the top right corner there is share, which generates an image, which allows you to generate an image from them. Which is precisely the reason why I've been wanting to keep this entire thing.
Yeah.
I will then reorganize.
Okay, well, yeah.
So that is...
I'm gonna head out.
That's fair, that's understandable. And...
Yeah, I was gonna say real quick. I'm gonna head out now. Thank you so much for having me, it's an honor.
Well, I appreciate the paper. Once again, available. I will try to spread around the word some more, and I hope that this kind of presentation was informative and gave good context on the paper itself. I think that will be it then. I will not keep you here any longer, and we might as well cut it short. Thank you so much for watching, and have a great day. Bye!